So a lot of what we do in this section is all going towards understanding what reactions look like and how we can predict the products or reactants of a nuclear reaction, and also talking about how we know whether or not nuclei are stable. And this slide kind of summarizes it. But with decay, we say we have unstable nuclei, right? Um, that simply means at some point it'll break apart. And so not every isotope of an element is a stable isotope. Some are unstable. For example, we spoke of uranium already. Uranium doesn't have any stable isotopes. So all the uranium that we have is slowly decaying away and being broken down into smaller elements. So large nuclei, right, tend to break up and form into smaller nuclei, and that the particles that come out of those have specific names or identifications that we talk about. We can pick up the particles that come out using something called a Geiger counter or a scintillation counter. And nuclear decay, there's actually two types of nuclear decay. One is natural. This is when we're talking about uranium, for example. And the other one is induced, where we take one nuclei and basically ram it into the nucleus of another atom to produce sort of what's called induced decay. And this is what I was talking about earlier with Rutherford. We talked about transmutation. Transmutation is induced decay. Okay, so when we take one type of element, we fire a nuclear particle at it, and then what happens is it becomes unstable, not because of the kinetic energy of the particle, but just because by its own structure it's unstable, and then that breaks up to give us new nuclei. Okay, so the types of particles are helium nuclei, which are known as alpha rays. I've mentioned those before. Beta minus is what there's a little minus sign down here. Beta rays are actually high-speed electrons. And then gamma rays are photons. And they're the highest energy types photons that we sort of categorize. They're on the very high end of the electromagnetic spectrum. And then there's the positron, which is an anti-electron. It's an antimatter particle for an electron. So beta rays are electrons, and positrons, you notice they have the same symbol, but they are known as beta plus. These are the anti-electrons. Now, some of you may have picked up on what I said, right? The nucleus breaks apart, and these are the particles that come out of it. So the first question you might have is, why are there electrons coming out of the nucleus? And so we're going to cover that. I mean, it's one of those weird things that nobody tells you. They've known it since they've known about the neutron, basically. But there are actually protons and electrons bound together that produce neutrons. And so when you break up a nucleus, you will see electrons coming out of the nucleus. Okay, so the 5 decay modes, for the most part, are named after the particles. There's alpha decay, beta decay, gamma decay, positron emission, and then the last one is electron capture. And electron capture is when a nucleus actually falls in, quote unquote, it's not really falling, right, but goes into the nucleus to convert a proton into a neutron. So here we have an example of a pretty common nuclear decay reaction. Polonium-210 decays into lead-206. I think it takes something like 180 days. I looked at it not that long ago. So it takes about 180 days, I think, for that to happen. So if you had a gram of polonium in about 180 days, you'd have half a gram. And then if you had 360 days, then you would have a quarter of a gram. So it follows the same kind of behavior that we talk about in like first order kinetics, and so we'll come to that here in a second. But when you look at those two, the decay mode you can predict by looking at the mass number and the atomic number. So for example, you know for the atomic number that 84 is equal to 82 plus what, right? Well, that should be 2, right? And what we say is that the atomic number and the mass number are conserved. So remember, 84 is the number of protons in polonium, 82 is the number of protons in lead, so what's missing is 2 protons. Now when we're looking at the mass number, we see polonium 210, right? So 210, that's equal to 206 plus 4. So what do we know of, right, that has 2 protons and 2 neutrons? Because remember, 4 is neutrons and protons, right? And that would be helium. So this actually, this reaction is actually not balanced. We can balance it by writing a couple of different forms of it, but most commonly alpha, right, 2 and 4. The 2 and the 4 can be left off for an alpha particle, but it helps in sort of interpreting what you're seeing. But this is 4 plus 6, that's 210, and then 4 plus 206 is 210, and then 82 plus 2 is 84, right? So mass number and atomic number conserve. So this allows us to be able to do a couple of different things. One is identify the particle that was released during the decay process. That's one possibility. But the other is we can do induced nuclear, like transmutation reactions. We can look at the incoming particles and look at the outgoing particles and predict which particles were released during the process, or what the particle was that was coming in during the transmutation reaction. So always when you do these, just write out the reaction in sort of an algebraic form like this, right? And then look up atomic numbers and symbols, and then that's how we sort of do nuclear reactions. Now, the atom on the left is typically known as the parent, and the atom on the right, not the subatomic particle, but usually the atom on the right is known as the daughter. And in some reactions, there's multiple daughters produced in the reaction. So let's just go ahead and just do a bunch of examples. Here's uranium-238 by alpha decay. So then I know that 238, right, is equal to some number x plus 4. And I also know that 92 is equal to x plus 2. And so I know this is 90, and I know this top one will be 236, like that. So in order to write out the symbol for the element that is produced in this case, right, we're looking for X here. All we have to do is look up the symbol for the element that's 90. So, right, you go on your periodic table. Oh, sorry about that. It's way down here now. 90 would be here. Right, uranium here. That's uranium. So there's thorium. So that's my element symbol. So it's thorium. This guy here is thorium. 236, and if you want to, you can drop the 90 in there as well. Again, the 90 is a little redundant, just like for the alpha particle, the 2 and the 4 are kind of redundant here. But this is actually another way that you can write it, or you can even write it like this. Although typically when we're talking about nuclear decay processes, it's not the electrons that aren't actually produced in that reaction. So that's why this is probably a better symbol, because helium-4 can be interpreted as a helium atom with the electrons. Here's another example, right? We have a nuclear reaction, a decay reaction. This is an example of a beta decay. So a beta decay is an electron, and the way we treat the electron is we give it a mass number of -0, and an atomic number of -1. So this number in the bottom left represents the nuclear charge. So we can write, for example, 131 is equal to something, right, x plus 131. Sorry, yeah, 131? No, what I got lost here. Hang on. 0 plus x. That was silly. I was already solving it in my head. So x is going to be 131. And then we can do for the atomic number that 53, right, is equal to -1 plus x. Well, x has to be 54. So the atomic number actually goes up in a beta decay process. And so this element would be have an atomic number of 54. So we go to the periodic table, look up element 54. So that's xenon, right? So now we can write Xe, and then it's got 54 down here, and then the top it has 131. Effectively, you notice the mass number hasn't changed, but the atomic number has, right? It's gone up. So effectively what you've done is this. Now, what's interesting about this process is it's sort of like a binding energy kind of situation. Like if you're going to split these two apart, there should be some energy associated with that. And it turns out there was another really small particle that was hard to detect, and that particle has later been called what's called a neutrino. And neutrino actually means little neutral one. So there was a particle that was released that related to the mass loss, right? And that mass loss was not really observed because it has a very small mass, and it also has a no charge, and so it was one of those things that's very difficult to detect. So let's look at gamma emission, right? Gamma is a photon. So how does a photon come out of a nucleus? So I guess a simple way to say it is it usually is something that follows a nuclear reaction, okay, a decay reaction. And you have a nucleus and it emits a particle. So in this case, we're looking at boron, right? So boron produces carbon-12 and a particle. So what is that particle? You could predict what that is simply by saying like this, 12, right, is equal to 12 plus 0, right? That's what I'm looking for. And then I could say 5 is equal to 6 plus what? And that's a minus 1. So my particle that is missing is a beta particle. And what that does is essentially causes the conversion of a neutron into a proton. So it turns out carbon-12, when you make it, if you think about how you're packing positive and negative charges together, right, isn't stable because it has to rearrange the particles to make it more stable. So you have this sort of process that produces this unstable nucleus, and then that unstable nucleus decays, ignore the X here, that just came over from here, decays to produce a more stable nucleus and a gamma photon. And because the forces within the nuclei for attraction are so strong, it produces actually quite a bit of energy. 0.05 electron volts is still a lot of energy. And so that ends up being in the gamma photon range that we see. So this little star refers to something that's called metastable, right? Metastable nuclei are only stable for a short period of time. So meta just means short in this case. And so it'll be produced and then very quickly decay by gamma emission to sort of allow itself to rearrange into a more stable form. Technetium 99, a lot of times you'll see reactions like this, right? Metastable technetium produces a more stable technetium nuclei plus a gamma photon. Now, interestingly, just kind of side note, right? This gamma photon that leaves the nucleus is used in like imaging studies for medical purposes. And technetium itself is always a man-made element. If you look on the periodic table, you'll notice technetium in the middle here, right, element 43. You notice how it has parentheses around its atomic mass, and that's because there are no stable nuclei of technetium. So it's actually a hole that naturally exists in the periodic table, and the only reason we can fill it ever or ever have any of this element is because we make it. So next we have positron emission, and in positron emission we have, again, think about the word emission, right? We're releasing a particle, a positron, from the nucleus, and so you can write a reaction as carbon 11 goes to make some unknown element. It's got little x's up here we don't know as well, plus a positron, and a positron symbol is beta plus, or beta like that. And what we do then is we, again, do the same thing we always do. We would say 6 is equal to an x plus, and then 1, that's the positive, right? So you can write it as this as well. And then you can also say then 11 is equal to x plus, and then the mass for a positron is 0, so sometimes you'll see a 0 up here, so we could say 0. And so the new element that we create has an atomic number of 5, so that means it's boron with a mass number of 11. Okay. Now, something that happens, and this follows the positron emission, is that a positron will fairly quickly find itself running into an electron, and when the two meet, they annihilate each other. Literally, you go from having mass to creating just pure energy. So if you want to know the energy for this reaction, the way you do it is you use the Einstein equation, and you assume the mass defect is the loss of the mass of an electron. So for this reaction, the way it's written, right, I could calculate it as E is equal to mc squared, right? So m is the mass of an electron, so 9.11 times 10 to the minus 31, but you lose 2 electrons here and you produce two gamma photons. So what I'm going to do is just calculate the energy per electron. This is in kilograms. Times 3.00 times 10 to the 8th squared. That gives you 8.199 times 10 to the negative 14 joules, and that's per photon because this is for just one of the electrons. So the overall energy, if you wanted to calculate the energy for this reaction, would be twice this number, because this is the energy just for one of the electron, or one of the particles being converted over to energy. If you wanted to know this in kilojoules per mole, you could calculate it using Avogadro's number. If you wanted to know the wavelength of light, right, that this particle has, then what you would do is simply go E is equal to h nu. This is the equation that you use for calculating the energy based on the frequency. And this is Planck's constant, which is 6.626 times 10 to the minus 34 joules times seconds. And the other form of this equation that's handy to know is based on the frequency and wavelength relationship for light, and it turns out the speed of light is equal to the frequency of the light times the wavelength of the light. You can rearrange that and substitute it into this equation. You'll also see this as a form of the equation. So that's to calculate the wavelength in meters. So there's a couple different other calculations that you should be familiar with that are possible, but these are mostly the kinds of things, the kind of calculations you do in Chem 1A. But anyways, when you do this, what you find out, it falls in the range of gamma photons in the electromagnetic spectrum. So next we have electron capture, and electron capture is a little bit of an oddball. So far, everything that we've done has been a product, right? So in a positron emission, we say emission because it's a product. In gamma emission, gamma photons are a product. Beta emission, beta products. Beta particles are part of the product. And alpha emission, right? Alpha particles are part of the product. But in electron capture, what we have is an electron being captured, so that means it's one of the reactants. So when you're doing an electron capture reaction, two things, really three things happen. An inner electron gets actually sucked down into the nucleus, and what that electron does is converts a proton into a neutron. Now, when that happens, there's a hole left, and the electrons want to go to fill the lowest energy shell, and so what happens is electrons will drop down and fill that hole, and the result is that photons have to be released, and typically these are in the X-ray range. Okay, so here's an example of a problem. We have mercury 201 is decaying by electron capture, right? What is the identity of the daughter nucleus? So it says decay, but that doesn't necessarily mean it's the product, and it's going by electron capture. So we have mercury 201, Hg 201, and it's going by electron capture. So you can write it as beta -1 and 0, or just beta is typically default for the electron. And then what's going to happen is whatever isotope I'm going to produce out of this will have a 201. But then the question is, what's the atomic number, right? Well, it's one less than mercury, so you need to look that up. And mercury is here at 80, so the product is going to be gold. So this is going to be 79, because, right, this is 80, -1 is 79, and then the symbol would be for gold. Okay, so what we're going to do next is look at patterns in nuclear stability. And this is one of those sections that is nice because there's not a lot to have to explain about it. And that is kind of bad because there's not a lot of explanation with it. It's just empirical information. That means based on observations of what happens during nuclear reactions. So I'll be saying stuff in here, and if you want a deeper explanation, I'm not going to give it to you, so I do apologize. But I'll talk to you about how we predict nuclear stability based on patterns that we see in the composition of nuclei. So the first one, right, the first three things that we're going to be talking about actually have to do with neutrons and protons. And so I'll be going through these one at a time. This is like a summary slide, but the first thing that we'll be talking about is that all nuclei whose atomic numbers are greater than or equal to 84, okay, are radioactive. So we go to the periodic table, and in the periodic table, that starts with polonium. So everything to the left, quote unquote, of bismuth that has an atomic number of 83 or less, or 84 and higher, right? 83 or less are stable, and 84 and higher are unstable. Okay, so in essence, right, you have a large nucleus, and it has too many particles to be held together stably. Eventually, it's going to decay. And oftentimes this happens in a series, that is, you get one decay and another decay that follows until eventually you get to a stable nucleus. So smaller, more stable nucleus and an alpha particle. So that's typically what happens with really large nuclei. The first thing they do is they start spitting off mass by spitting out alpha particles. Now the second things and the third thing that we do seem closely related, and they are. One is the neutron to proton ratio that we'll be looking at, and the other one has to do with odd numbers of neutrons and odd numbers of protons. So what I wanted to talk to you first before I explain to you neutron-proton ratios. This is a graph that is not from your book, but it's like my favorite graph of this whole kind of phenomenon. And what it shows half-life stability. So that means basically if it's stable, it never decays. And as you get down to this blue region, these are very, very unstable. They have essentially half-lives that are less than a second, so from about blue on down. That means if you had 1 gram now, a second after, you would have half a gram, and then a quarter gram, 2 seconds, eighth of a gram at 3 seconds, etc. On the other hand, some of them are very stable, right? Not stable, but very stable. So if you had a gram now, in 10 to the 14th years, you would have half a gram. Okay, that's a long, long time. So I have long, long half-lives. So what they do is they take all the known isotopes and they graph it according to where they fall by color on a line. So this is the number of neutrons. This is the number of protons on this axis. So you see Z and N. And you'll see there's a black, like in the middle of this whole thing, there's this sort of black line that goes up like this, right? And then it stops right here, right? This is the 84 that we were just talking about. There are no completely stable nuclei from 84 on up. So that's why you don't see the black line. It disappears here. And what you end up with is just a bunch of unstable nuclei. Still some relatively stable nuclei, because you can see these ones that are in red, right, and even in green, are above a year. And this is exponential or logarithmic, so it's going up quite quickly as you go up this way. But the idea is this. It appears for atomic numbers less than 20, the ratio of protons to neutrons should be about 1 to 1. In other words, if I'm looking at helium, helium's a good example, right? It has 2 protons and 2 neutrons, which means its net mass number is 4. It falls right on the 1 to 1 ratio. On the other hand, and on the same hand, I should say, really, if you look at neon, right? Neon has 10 protons and 10 neutrons, so its mass number is 20. Again, these both fall under the 1 to 1 category, right? This is right in this range here so far. And if you look at calcium, and this is the very end of it, right? Calcium has an atomic number of 20, and the isotope, the stable isotope of calcium that has the greatest abundance has a mass number of 40. Again, it's in that mass ratio of 1 to 1. Then once you get past, the neutron-proton ratio of 1 to 1. Once you get past 20, so this is calcium here, then there's a sudden deviation that starts to move upwards. And in essence, what this line is telling us is it's very hard, or gets harder, to keep the nucleons together. And so it requires the protons. It requires more protons than neutrons in the nucleus. It goes to about 1.5 when you get up to about 100 here. So we'll go up to 100, right? And then this number is 150, so that's where the ratio of 1.5 comes from. It's basically 1.5. You notice this is pretty straight up here. This is basically about 1.5 all the way from about, 70 or 80 on up. But it falls to about 1.25 in this middle region over here. So you can actually look at the neutron-proton ratio of an isotope and guess where it sits on this line to predict whether or not it's going to be more or less stable. Okay. Now, another interesting phenomenon that we see in neutrons and protons, and I'll come back to this and we'll do some examples, is this one. It's whether or not there are even number of neutrons or an even number of protons, or both. So you take all the stable isotopes, right, and you put them on a bar chart like this. And I have neutrons that are either odd or even, and I have protons which are either odd or even. And what you'll notice is out of these 200 or so isotopes, right, only 5 of those, about 2.5% of them, are stable, where the neutrons and protons are both odd. It's it's similar to the idea that electrons like to be paired in orbitals. But the most common combination is when you have an even number of protons and an even number of neutrons. Most of the stable isotopes have that combination. So if you're looking at an atom and trying to predict whether or not it's stable, you could look at neutron-proton ratio, and you can also look to see whether the number of neutrons and the number of protons are even numbers. The last thing that I wanted to point out has to do with magic numbers, right? And this sounds pretty hokey if you ask me, but what magic numbers represent, right, is that there are specific numbers of protons and neutrons which appear to be exceptionally stable. And those are 2, 8, 20, 28, 50, 82. And these numbers are the same for protons and neutrons. And the only one that's different is the 114 and the 126 for protons and neutrons. There's this model of the nucleus. It's like, Bohr's model, orbital theory, right? Stuff that we talked about a long time ago. And we have these shells where electrons reside. Well, it turns out there's a shell model for the nucleus as well. And in that shell model, right, these are like the octets. If you remember, the octet rule comes from the number of orbitals that exist. Well, there's a similar kind of thing for nuclei. And these are those magic numbers. So if a nucleus, like helium, right, has 2 protons and 2 neutrons, it's going to be especially stable. On the other hand, if you have 82, for example, and the other number is not 82, you're still very stable simply because you have the magic number of protons. Where we see this in the larger elements that's interesting is that elements like tin, right, which is element number 50, that's this guy right here, because the 50, atomic number of 50, gives the tin a lot of stability, there are actually 10 different isotopes of tin that are stable. So the fact that protons are 50 allows there to be a number of combinations of neutrons that are also stable. So what we've talked about so far, you can look at neutron-proton ratio. You can look at odd and even numbers of neutrons and protons. And then there's this magic number, which is again related to protons and neutrons, which help us to identify stability in nuclei. So the last thing I wanted to talk about in this section is how we can use the neutron-proton ratio to help us predict which are the most likely ways that a nucleus will change, decay, in order to get back to the band of stability. Okay, so let's think of yourself as, let's say you're here as an element, and that's your neutron-proton ratio, right? So in essence, what you need to do is you need to decrease the number of protons that you have, and at the same time increase the number of neutrons. So in a sense, in this chart, what you need to do is, starting here, move in this direction and this direction. So what does that imply? Well, if you're below the band of the stability, what you're going to be doing is thinking about is like an electron capture reaction. So you have a proton, right, plus an electron to make a neutron. That'll effectively move you in that direction. If you're above the band of stability, up in here somewhere, right, your goal is to drop in number of neutrons and go towards the right like that. So what does that mean, right? So if you take a neutron and you convert it into a proton, then what you have to do is you have to spit out an electron in that process. And so that is a beta emission that takes place by converting the neutron into the proton. Okay, so this is the beta particle. So we have fluorine 19 is the stable isotope. What would I predict for fluorine 22, right? So in essence, if you're thinking about where you are on this chart, this is atomic number 9 here, so this is fluorine 19. Remember, it's protons plus neutrons that gives you the 19. Well, if you're 22, right, that means you have too many neutrons, so you're above the band of stability in that sense. So if you're above the band of stability, what you'll want to do is drop the number of neutrons and increase the number of protons, which means most likely you'll do something like this. For this part, so most likely going to be doing a beta decay. Like that. Okay, so anyways, that's just another way that this band of stability can be useful. If you're trying to Google this and you're looking for it, it's called the band of stability, sometimes referred to as the belt of stability. And you should be able to find a lot of information based on that.